Okay, this video covers the basics of something that we call node voltage equations. Node voltage equations are a way of systematically writing equations that help us solve for a circuit. Okay, so it's very systematic. It's a technique that we can apply to a large number of circuits. We're going to simplify the things that we apply it to in this class, but I think it's kind of an important topic because it's a systematic way of writing equations. Okay, so we saw a similar thing that happened when we looked at static equilibrium, when we looked at sum of forces in the x direction equals 0, sum of forces in the y direction equal to 0, and the sum of moments about any point is equal to 0. So we could systematically approach a problem and write the equations and solve for that particular system in static equilibrium. We can do the same thing with electric circuits. We can systematically apply the equations, solve them, and then once you have these node voltages, it turns out anything else in the circuit is really a piece of cake to get, all right, once you know the node voltage equations. All right, so voltages are trickier things. I've talked about before the idea of the analogy with gravitational potential. Okay, so I've got this diagram labeled here. Think of this as the blue part is sea level. Okay, so here's sea level. And we're looking at different elevation changes. All right, so I've drawn this on the grid, so let's assume, for discussion purposes, that one grid line is 100 feet. Okay, so I could take a look at these elevation points with respect to sea level, and for example, I could read off that EA is, and I count this up, 500 feet. Okay, I could get EB, count that up, 800 feet. And finally EC is 200 feet. All right, well and good. So I think it's obvious that if you wanted the elevation difference between points, you could just subtract the actual elevations, because we know that they're with respect to the same reference, and because they're with respect to the same reference, the differences will work out. All right, so for example, it's really obvious that EB is 300 feet higher than EA. All right, so if I wrote this out, let me move this out of the way, we use this for reference. If I write EBA, all right, this is now an elevation change between 2 points, and it's given as an elevation that's only referenced back to 1 point. Okay, so we didn't write this as EAR for reference. Okay, we just called it EA, with it being understood that the reference point was some point that we chose. In this case, we chose sea level. All right, so if I wanted EBA, the elevation difference between point B and point A, you could get that by just writing EB minus EA. Okay, and so that would work out. 800 minus 500 is 300 feet. Because that's a positive number, we would have the interpretation that point B is at a higher elevation than point than point A. All right. We could take a look at a different combination. Let's take a look at ECA. All right. Because the C is first, we would put EC minus EA. EC is 200 feet. Then we subtract EA, which is 500 feet, and we get minus 300 feet, which is all well and good, because what that tells us is that point C is negative 300 feet higher than point A. Okay, so the negative sign flips the interpretation, and so we would say equivalently that the elevation at point C is lower by 300 feet compared to point A. We're doing the same thing with voltages, okay? We're looking at different points in the circuit. We choose a reference point that's equivalent to the sea level thing. Remember, voltages are always across something, right? Not through something. All right, current is what goes through the elements, it's voltage that goes across. Okay, one other point I wanted to make is what happens to the elevation in flat spots, okay? So I could take this point and pick it up and slide it over. I say I can do that. I'm trying to do that. Okay, when I slide it over, if I slide it over something flat, there is no elevation change. So EA is equivalent here as it is here. Okay, EA is the same here, 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 and here. All right, but if I start to climb the hill, all bets are off. That's no longer EA, right? That's a different elevation. Okay, so what happens when we do node voltage stuff is I talk about sliding points along a wire just to help us figure out how to write these equations. All right, so I slide the points. As long as the point is sliding along a wire, there's no voltage drop across a wire. So the voltage potential is going to be the same as I slide the dot. Okay? All right, so hopefully that helped you to get started with visualizing how we're going to do node voltages. Let's jump right in and talk about it. All right, so when we are looking at this, we take the nodes to be the places where you have circuit branches connecting together. Remember we talked about branches where you have elements connected. For example, let me switch this to green. Here is a circuit branch. Okay. All right, so a series connection of elements. All right, so if you have, I think technically you could call it 2 or more. It's usually 3 or more branches that connect to form a node. All right, so I see here that there's a node at point A, and then we've talked about this before. I like to draw circuits a little more squared off. All right, but you could delete these lines here. All right, and connect them because there was no element in between. I could connect them all at a single point here and call that the reference. All right, that's equivalent. All right, so essentially I have a node. I'm going to draw all the nodes in red. A node here, a node here, and a node here. All right, so I have 3 nodes. I'm going to reference those. I'm going to call this one VA, this one VB, and this one is going to be the reference. And usually I draw a little arrow that indicates where the reference signal is, or the reference node would be. All right, sometimes people will draw a ground symbol, okay? I think it's technically more precise to just draw an arrow. Okay. All right, so hopefully you're with me. We have established what a node is. Okay, it's where 3 or more branches connect together, 2 or more branches connect together. And then we found all the nodes in this simple circuit, and we labeled them. All right, we chose one of those as a reference. Okay, so the node voltage technique depends on writing KCL equations at each node. All right, so I'm going to go through it. I think it's easiest to learn this just by example, and if we do enough examples, you'll pick this up. All right, it's very systematic. It is not hard to write the equations. All right, sometimes it's tedious to solve the equations, but writing them should be pretty straightforward for you. Okay, so let's get started. All right, so what I'm going to do here is, the way I usually do it is I reference all the currents coming out of the node. All right, I try to be very consistent with that. So remember when we did trusses, I told you that what I like to do is reference all the forces pointing, I can't remember, away from the joint or into the joint. I like to do them the same way every time, all right? So let's go with currents going out of the node, all right? So I'm going to label these currents. I'm going to start with node A. All right, I have the voltage with respect to the reference, so this would be plus and then minus. If I took a voltmeter, connected the minus sign to this point and the plus sign to this point, it would read VA, okay? All right, so next thing I'm going to do is I'm going to label the currents. All right, so I'm going to draw those in red. All right, here's a current. I'm going to call it I1. Here's a current, I2. And here's a current, I3. All right, and what we know from KCL is that I1 plus I2 plus I3 is equal to 0. Okay, so from there, it's just a matter of doing the currents, finding out the currents. All right, and so this is where I like to talk about sliding the dot. Okay, so if I take this reference dot, all right, I'm going to redraw it right here. I'm going to make it bigger, right? Pick it up and slide it. Okay, I could slide this reference dot, and it's still, it's just sliding along the wire. All right, in the elevation example, this would be sea level. It'd be sliding along the surface of the sea. All right, so we take the reference, and I can slide it all the way up, and I like to mark that as the reference is 0 volts, just like sea level is 0 elevation. Okay, so this would be 0. Okay. On the other side, I can also label a point, all right? And because there's a voltage change, what would that be labeled? Well, it's a voltage rise of 10, so this dot, I can label that as a 10, okay? And if I wanted to, I could pick this up and I could slide it over to be right next to the, slide the dot over. I didn't draw it big enough. Okay. The voltage is labeled 10, and I can pick this dot up and slide it right next to the resistor. Okay, so a lot of times you do this mentally, you don't actually physically move the dots. Okay, but now I'm going to also choose this dot. This dot is VA, right? This dot is 10, right? I slid it along a wire. If it started out at 10, it stays at 10 because it's along a wire. It's like sliding along a flat plane of a flat part of an elevation. Okay? All right, so I take VA and I slide that to the other side of the resistor here. I just can't, I don't have these fine enough. Okay, so I slide that to the other side of the resistor. There is point VA. Okay, so I know that's VA and I know that's 10. I can now calculate a voltage difference across the resistor. All right, and here's where we need to use the passive sign convention. Okay, we talked about the passive sign convention is where you have a voltage drop in the direction of the current flow. Okay, so because we're using a resistor, we know resistors are passive elements. We use the passive sign convention. We put a plus on the first side of the dot and a minus on the second side of the dot. Passive sign convention. And we say that's the voltage across that resistor. And so I can write down the voltage across the resistor as VA minus 10. All right, so VA minus 10. And then according to Ohm's law, if I just divide by the resistance, I would have I1. Okay, so the resistance in this problem was 4. All right, so boom, I'm done. I calculated I1. All right, let's do the same thing for I2. All right, so before we do that, let me clear all the currents. All right, we're going to start over with the labeling. I don't want to start that far over. Okay, so we're going to now look at I2. Okay, all right, so to get I2, I can slide the dot. Right, so if I slide the VA dot, VA is, I'm going to move I2 coming down here, right? Here's I2. Here's the VA dot. This is VA. If I slide the 0 dot, that slides up to here. So the voltage across the 6 ohm resistor is VA minus 0. And then to get I2, I divide by 6. That's just Ohm's law. Boom, I've got I2. All right. And now, I'd reference these. I erased these too soon. I reference this coming out as I3. Okay. How would I get I3? Well, there's no resistor in that branch, so I can't use Ohm's law. All right. But fortunately for me, this is a current source. It's 2 amps. So I know what I3 is. I3 is just referenced backwards from the direction of the independent current source. So I3 is -2. All right, so there's the node A voltage equation. Okay, let's switch to purple and let's do node B. Okay, so for node B, I have a similar approach, okay? At this point, I just ignore all the other markings that I have on the circuit and I redraw the currents, okay? So I would call this coming out I1. I would call this coming out, I'm mentally doing this, I2. Technically, if you're an engineer, you'd want to be precise with the labels, okay? So I could call this something else, like IA, IB, all right? You see why I want to do something different? Because I already used I1 and I2. All right, so we label these IA plus IB plus IC. All right, what we know from KCL. All right, it's a quiz question. What do we know from KCL? All right, so at this point, what we know is all the currents coming out of the node, IA plus IB plus IC are equal to 0. Okay, cool. All right, so next we just need to find what IA, IB, and IC are equal to. All right, so my favorite one on this list is IA because IA is the same branch current as the independent current source. So immediately I write down that IA is 2. All right, then when I get to IB, all right, IB is a matter of sliding the dots. Okay, so here's a dot. I can make it a great big dot that I can slide at the reference node. All right, so I grab the dot. Okay, and I slide it. I say I grab the dot. I slide it and I put it on one side of the 2 ohm resistor. Okay, and what is its value? Well, it started out at 0 volts. Right, it's still 0 volts as we slide along a flat spot on the mountain. Okay, this is 0 volts. All right, same thing with VB. This is VB. If I pick this up and slide it down, I just can't do it. Well, you get the idea. Picture this sliding down. All right, it is still at voltage VB. So I put the dots on either side of the resistor, and which way does the current flow? The current flow is referenced down. So which side of the resistor is plus? Well, I use the passive sign convention, plus and then minus. All right, so that tells me I need VB first and then subtract 0. You do the plus terminal first, subtract the minus terminal, and you divide by the resistance. In this case, it's 2. All right, so boom, we've done IB. All right, so next let's look at IC. All right, so with IC, we'll go to another color. Let's go to green. Okay, so I take the dot and I slide it over and I move it to here. It's 0 volts, right? I started at 0, it slides along, it stays at 0. Okay. What is it on the other side of the 6 volt source? Well, that's an elevation change. It's a voltage change. So it goes up by 6. So this dot is 6. All right. Now I take this dot VB. All right. I know it's VB because it's that node. I slide this dot over to the other side of the resistor. I've got it. I've got the current. As long as I know the voltage across a single resistor, I've got the current. All right. Okay, so if the current is referenced away from the node, so remember I talked about that, to do IC, it's referenced away from the node. All right, this would be the plus and this would be the minus because we're using the passive sign convention. You put the plus and the minus in the direction of a voltage drop. Okay, so that means I take the dot, that dot is VB, I subtract 6, all right, plus VB minus 6, and I divide that by 3 equals 0. Okay, so at this point, you know, here's the process we learn as we go through engineering. We have one equation here, we have a second equation here. VA and VB are unknowns, okay? In this case, it's pretty simple because they're single equations that let you solve them, all right? But I could solve this pretty easily for VA and VB, all right? So that's the node voltage technique illustrated with a simple problem. We'll do more of these so that you can figure out what to do, and then we'll throw in some twists. Like you could put 2 resistors in a branch, okay? If you put 2 resistors in a branch, what do you think you would do? Well, you know, the preview of that answer is if they're in the branch, they're in series, and so you can you can come up with an equivalent circuit and replace that branch with an equivalent circuit. All right, but we'll do more of those, and you'll see how to write node voltage equations